we already starting with the introductions. Okay, what we have done, we have proceed with introductions. Okay, with introductions, and after that, nomenclator, how we can name the compounds. Okay, and after that, proceed with the definition of alkyl halides, definition of nucleophile, and we goes introductions about the nucleophilic substitutions. They have two types of nucleophilic substitutions, which is SN1 and SN2 reactions. Okay, what is the difference between them? And after that, we start also regarding discussing about the SN2 mechanisms. We start with SN2 mechanism, which is this one is quite important. Okay, and now we try to finish by today, and I will provide some questions and we will discuss during the lectures. Okay, don't worry. Don't worry too much, because for me, my approach is playing around with a few examples and questions, and to make sure everybody can catch up. So this one is done. Okay, so we go to the next slide. 47. 47. Now we will go for the 47. Okay. In SN2 reactions, I just revised whatever we discussed about this one. So in SN2 reactions, they have two examples showing the inversion of configurations, which is referred as stereogenic center. So the first one is okay. If we see clearly this one is at the back. This one is at the front. Okay, so this is the Kira center. Okay, so we will see this is a nucleophile. This is a nucleophile. Okay, nucleophile. Nucleophile will attack the Kira center, and after that, there have be inversion configurations. And meanwhile, if the Kira center, okay, because the leaving group, if we see clearly here, okay, the leaving group is on the plane. Okay, if we see clearly here, it's okay. The leaving group is on the plane. Okay, so it's become like this. Yeah. And if the leaving groups in the back and front positions, if we see clearly, chlorine is a leaving group. Leaving groups, okay, chlorine is a leaving groups. The nucleophile will attack the Kira center, and also the inversion configurations may happen. Okay, so this is two configurations. One is the leaving group is on the plane, okay, which is this one, and one is a leaving group at the back and at the front position. So they have different in terms of arrangement, so be careful. What I can say is SN2 reaction involve inversion configurations. Okay, so it's depend on also the substrate reactivities. Okay, the number of R, which is referred as whether they are methyl. Okay, there's methyl group here. Okay, the second one is the primary. Okay, the primary, this one is secondary. Okay, and the last one is the tertiary. So so if we see clearly, okay, from methyl to primary, it will increase the rate of SN2 reactions. Meanwhile, tertiary doesn't not really involve or doesn't really involve in SN2 reaction. This is very important. So this one is the reactive. This one is non-reactive. This one is it. Okay. So as usual, so this is common conclusions. Okay. So methyl and primary alkyl will go easy for the SN2 reactions, but you have to consider what types of nucleophile and also whether what is the solvent, whether they are protic or aprotic. So don't forget about these terms. Okay. So the second alkyl halide will react more slowly. Okay, meanwhile the tertiary alkyl halide does not go okay for SN2 reaction due to the steric hindrance, because this is the substitutions which is the bulky effect, so it doesn't go to any substitution reactions. But because and for the steric effect in SN2 also represent of the electron cloud here, electrostatic potentials. You can see the electron clouds. You can compare between the size of electron cloud between tertiary. This is the tertiary one, okay, the tertiary, and this is the secondary. Okay, this one is primary, and this one is methyl. Okay, so for sure there will increasing reactivities from primary and methyls. Meanwhile, tertiary doesn't go any SN2 reaction. So okay, this is a kind of summarize that we can conclude for the SN2 mechanisms. The first one for the kinetic is a second order reactions, is depend on the both concentrations, which is this one is the alkyl halide. Okay, yeah. This one is alkyl halides. Okay, alkyl halide. And this one is concentration of nucleophile. If we increase one of them, so if we increase 10 times, the reaction rate will be increased 10 times. Okay, so this is one-step reactions. It represents with one-step energy diagrams. Okay, so for the stereochemistry, they have involved inversion configurations. If you have highlighter, you can highlight here inversion configurations, and also they are doing backside attack of the nucleophile. Okay, if you have a highlighter, you can do it. So then identity of R, it's unhindered halides reactors fast. Okay, they can be concluded by these arrangements. So primary and methyl also will doing faster compared to the secondary, and also the tertiary doesn't involve any SN2 reactions. Okay, this is an example of SN2 reaction in synthesis of commercial drugs. Okay. This is the ethambutol, usually used for asthma patients. Okay, ethambutols. If we see clearly, they have alkyl halides. Okay, alkyl halides, and also this one is nucleophile. Okay, this is also nucleophile, and this is a alkyl halides. Okay, it will go SN2 reactions. Okay, spontaneous reactions. So they will make a new sigma bond, which is here. Okay, the red color. Okay. The next examples will be Prozacs. Okay, another drugs, commercial drug. There will be the Prozac. So this one is the alkyl halides, and this one is a nucleophile. Okay, so it's a one-step reactions. They will get another products by doing some modifications. If we add these functional groups, and you can get a final products. Okay, this is one of the first of reactions that we learned during our studies. Okay, next go to the SN1 reactions. We already previously discussed about the SN2 So we are going the SN1 reactions. Okay, the mechanism of SN1 reaction will be drawn as the follows. Okay, so first they are removing them. Remove, eh? Okay, they are doing heterolysis. Heterolysis is they are breaking this bond. Okay, so they're breaking this bond first, which is the slow reactions. Okay, and form the carbocation. This is very important. Okay, so it's mean the alkyl halide will be a predetermined step. So, and after that, this one is the nucleophile. Will attack the carbon divisions if we know, oh my God, sorry for my drawing. What's happened? Okay, if we know that they have, if we see clearly the carbocations, it will be on planar. So the planar shape will be like this, right? Carbocations. So you have the empty orbital like this. So the nucleophile have the probability to attack from the tail, from the top, and from the bottom. So it could be different products. Okay. So the secondly nucleophile attack. Okay, nucleophile attack the acetate as a Lewis base and the carbocation as a Lewis acids. And this is second chapters. So we'll form a new CO bond, which is a sigma. Okay. So bear in mind that SN2 reaction have two-step reactions. So the first one, SN2, have one-step reactions. So for this one, SN1, they have two-step reaction. The first will be formation of carbocation. The second, a nucleophile attack. Okay. And during the carbocations, we can classify as a carbocation this carbocation. Okay, as a reactive intermediate. It's very reactive. Okay, so for here, for this, it's better doesn't use any water or base because it can involve in reactions. So SN1 reactions is a second order kinetic. Okay, it's also unimolecular because it's involved. If you have highlighter, you can highlight here. Alkyl halides concentrations. Okay, so identity and concentration of nucleophile have no effect of reactions rate, and also the nucleophile doesn't appear in the equation. So if you understand SN1 as a prime first order kinetic reactions and unimolecular, so it's also involved the alkyl halide. So you have to, if you can write the rate of reactions for this one, so it will, and you can answer any question that will be asked you. Okay, so rate equal to K, only the concentration of alkyl halides. Okay, so the energy diagram, because this is they will involve the formation of carbocation, which is very reactive intermediate. So this is the carbocation that I said. So they have two loop. Okay, this one is a transition state 1, and this one is transition state 2. If we ask you to draw the energy diagram, so usually we will provide the delta E activation energy. So we will give you activation energy 1 and also activating energy 2. From there, you can draw easily the energy diagrams. And don't forget what is the y-axis. Okay, what is x-axis? And don't forget delta G, H overall. Okay, they have two, because they have two loops. Okay, chapter 6, they have two loops. So you have two energy diagrams and also two delta H. Okay, from there you can do calculations for delta H overall, and you can come up with some conclusions whether there is exothermic or endothermic based on the delta H overall. Okay. For the stereochemistry of SN1 reactions, okay, to understand the stereochemistry, it's involved you have to examine, okay, the geometry. Okay, if you have highlighter, you can highlight here. the carbocation intermediates. Okay, so you have as I said, you have orbitals sp2 orbital hybridized. So it's the geometry will be trigonal planar. Okay, previously in the beginning we have sp3 tetrahedral, and after we remove the chlorines, the halogen groups, so it's become sp2. Okay, this one is tetrahedral. It's become trigonal planar. So it means S, yes, P1, yes, P2, yes, P3. P3, it's an empty orbital of P. So they have a possibility for nucleophile to attack from the top and from the bottom. So okay, as we see in these diagrams, first they have to lose the leaving groups. If you have highlighted, you can highlight here. And you, after that, you generate the planar carbocations, trigonal planar carbocations as a Akira compounds. Okay, so this is a planar carbocation. So the second step, the nucleophile can occur at the site. Okay, nucleophile attack. Okay, it can attack from the fronts and from the backs, and normally they will give two products. If we analysis this, and after that you can know this is two different products because of stoichiochemistry. And after that you can naming by using what you have learned in chapter 5. Okay, so this is very important. Okay, if the carbocation involve form in the Akira center, so non-Kira center, so there doesn't have any difference. If, for example, if the chlorine is here, okay, and also the proton is here, it will be different. Okay, so just be careful when you get the questions. Analyze everything, the possibilities, and hopefully you can come up with a very good answer. Okay. Okay, this is just an explanation about this one. Okay, and both compound will give you a racemic compound, a mixture of two compound with equally amounts. What I can say is a 1-to-1 ratio. Okay, but it's depend on the nature of the compounds. So, okay, this is another example. So, okay, nucleophilic substitution starting material for SN1 form a racemic mixture of two products. Okay. And with water, which is neutral nucleophile, initial products of nucleophilic substitutions lost a proton from the final products ROH, which is we will discuss in later about this. Okay. The substrates of reactivity of SN1 reactions is different with SN2 reactions. In this case, okay, this is more rapid. This is the reactive species. Okay, this is non-reactive species. Okay, so it's vice versa. It's favorable to the tertiary acyl helix compared to the methyl and also primary acyl helix. Okay, SN2, SN1, methyl, and also primary SN1 reactions is only for tertiary. But for the secondary, it's have the middle probability. So because it's both SN1, SN2, we react slow. Okay. This trend is exactly exponentials or opposite with SN2 reactions. So this is a kind of characteristic of SN1 mechanisms. Okay, as a conclusion, this is the first order kinetics, which is rate depend on the concentration of acyl helix. And also this two-step reactions because it's involved first it's involved the formation of carbocation, follow the nucleophilic attack from the top or from the front or from the back. So and also the substitution halides react fastest starting from the tertiary, secondary, and no reactions with methyl and primary. Okay, it's a opposite with SN2 reactions. So for the carbon cation stability, okay, the effect of the types of alkyl halide on SN1 reaction rate can be explained by considering the carbocation stability. Okay, for the SN2 is depend. We can argue with the bulky size of the tertiary. So that's why the tertiary alkyl halide doesn't involve SN2 reactions. But for the SN1 reactions, the carbon cation stability is more favorable for the tertiary. This is the tertiary, okay, compared to primary. So this is the explanation about this one. And also the number of R increase, the carbon cation stability increase. I hope you understand about this one. So for the inductive effect and carbocation stability, the order of carbocation stability can be rationalized through the inductive effect and hyperconjugations. Okay, and inductive effect occur by the pole of electron density through the sigma bond caused by electronegativity difference between atoms, and alkyl groups are electron donor groups that stabilize a charge because they contain several sigma bond, each contain electron density. Okay, and also as a result, alkyl groups are more polarized, okay, than the hydrogen atom and better to donate electron density. So in general, the more alkyl groups attached to the carbon with the positive charge is more stable than carbocation will be. Okay, so it means the tertiary carbocation will be more stable compared to the secondary, primary, and also methyl. This is the explanations about the stability of carbocation. So yes, okay, this is a carbocation stability, okay, explained by increasing the number of electrodonating, which is the R, okay, will increase the carbocation stability. And also it will can be explained by electrostatic potentials if we see clearly the map of the carbocations. For the hyperconjugations and also carbocation stability, okay, the order of carbocation stability also consequence of hyperconjugations. And also hyperconjugation is spreading out of charge. Okay, spreading out of charge. Anybody who have highlighter, you can highlight here by the overlapping the empty p orbitals, okay, and the adjacence of sigma bonds. Okay, this one can be explained by this, okay, because they have interactions or hyperconjugations between this is the orbitals. P orbitals, empty. P orbitals have the interaction with the sigma bonds, so that the charge will be spreading out and also form the hyperconjugations. Okay, and also okay, this overlap delocalize. Okay, anybody you have highlighted, you can highlight here, delocalize the positive charge. And also they will stabilize. Okay, so this is an examples. Okay, I already explained in detail, and so this is kind of explanation for this. So for the Hammett postulate, okay, the Hammett postulate relates reactions rate or to stability. It's provide quantitative estimate of the energy of the transition states. Okay, so in this postulate, the transition state of the reaction resembles the structure of the species, which is whether they are reactant or products to which of closer to energies. Okay, so the rate of SN1 reactions, okay, increase the number of R in carbon atom increase. So for example, okay, the stability of carbocation increase as the number of R group increase. So this is explains about the carbocation stability. Okay, increasing rate of SN1 reactions will increase the carbocation. Okay, it's clearly stated that tertiary carbocation, which is here, okay, more favorable to do SN1 reactions because of carbocation stability, and they will explain also the Hammond postulates. Okay, for Hammond postulate and also SN1 reactions, okay, the rate of SN1 reaction increase as the stability of carbocations. Okay, if we talk about the SN1 reaction, it's also almost discussed about the stability of carbocations. So if you can pick the ideas, SN1 reactions involve stability of carbocations, so tertiary carbocation is more favorable. Okay, so and also for here, for example, for the first step, we know that the rate of reactions rate is K concentration of alkyl halide. So of course, this is the rate determinant step because it's involving the formation of carbocation. You remember, right? The first mechanism is formations carbocation, and second mechanism is nucleophilic attack. Sorry, I'm just using drawing pad, so sometimes it's happen like this. Okay, and we can say this tertiary carbocations we do fastest reactions, okay, because they have stable carbocations. Anybody who have highlighter, you can use highlighter. Okay. So transition states, energy, and Hammond postulates. Okay, if we see here, this one is the. If you remember again, chapter 6, you can see they have two types of energy diagram. The first one is endothermic reactions. This is the endothermic reactions. Okay, the transition states resemble to the product more. Okay, because the activation energy is lower. Okay, so for the exothermic reaction, the transition state resemble into reactants. So they are going back to reactants compared to endothermic reactions. Okay, so as a conclusion for these two diagrams, okay, the transition state of endothermic, and if you have highlighted, you can highlight here, resemble to the products, more favorable to products. For the exothermic reactions is more favorable to reactants. Okay. So endothermic reaction in transition states, okay, like a previous slide, okay, an endothermic reaction, the transition state resemble the product more than reactants. So anything that stabilize the product stabilize the transition states also. So thus lowering the energy, activation energies, okay, and will increase the reaction rate. If there are two possible products of different stability in endothermic reactions, the transition state leading to the more stable product is a lower in energy, so these reactions will occur more quickly. So for the transition state energy of endothermic reactions, we can see here, okay, they have okay, if you remember chapter 6, the formation of the rate of reactions is depend on the energy activations. If you have lower activation energy, the reaction is become faster. Okay, so for the exothermic reactions, okay, there's another energy diagrams. Okay, the transition state resemble the reactant model products. They are more favorable to reactants compared to the products. So it's lowering the energy of products and no effect energy of a transition state. So activation energy is unaffected. The reaction rate is unaffected. And the conclusion that exothermic reactions is more stable product may not form faster since activation energy is similar for the both products. It will take it's a slow reactions, okay, and this can be explained by these diagrams, okay, because for the activation energy is similar for the both pathway, so doesn't give any difference. So for the application of Hammond postulate to SN1 reactions, okay, in SN1 reaction, rate determining step is the formation of the carbocation, which is anybody who have highlighter, okay, it's endothermic reactions, okay, and also according to Hammond postulate, the stability of carbocation determine the rate of its formation. So for here, this is the secondary alkyl halides, and this is the tertiary alkyl halides. So as we know, they are favorable to the more stable carbocations, which is carbocation tertiary, which is this one compared to this one. So if we ask you to draw the energy diagrams, you can represent energy diagram like this. Okay, so because the tertiary carbocation, this is the tertiary. Okay, anybody you have pen, you can write here. This is the secondary. Okay, so this one activation energy for the tertiary carbocation is lower compared to the secondary. So this one will be the tertiary will be react faster compared to the secondary carbocation. Okay. It's already explained here. Okay, so reaction 1 is low. Okay, so predicting the mechanism of nucleophilic substitution reactions, they have 4 factors. Okay, if you have highlighter, you can highlight here. There are 4 factors relevant in predicting whether they are going. This is very important. Okay, sometimes we are going reaction diagrams or reaction schemes, so we want you to draw the products or the proposed structure or doing the mechanism. This is the rules that's coming for. Okay, the first one, there are 4 factors here. The first one is you have to determine the alkyl halide. Okay, so the second one, you have to determine the nucleophile is strong or weak. Okay, this is a chapter 2. And of course, chapter 7. Okay, so this one is living groups. Okay, here, living groups, whether good or poor, depend on size. Usually, living group we are referred to the halogen groups. Okay, halogen groups. Okay, starting with fluorine, finished by iodine. Okay, 17, group 17, right? Hello. Group 17. And lastly, you have to check whether the solvent that you use, which is a protic or protic solvent. This is very important. Okay, they have 4 factors, so you have to list down everything, and after that make adjustments. So I already prepared some questions, so maybe we can discuss during the next class. So For example, nature for alkyl halides. Okay, most important to identify of alkyl halide, the first one, I guess. Okay, so increasing alkyl halide substitutions favor SN1, of course. Okay, decreasing alkyl halide favor SN2. So for these two, methyl and also, okay, for these two, A and B, we favor two SN2 versions. Meanwhile, for this one, for the number one, favor to SN1 because of stability carbocation. This one is list stability carbocation. This one is stereo effect. Okay, this one have 50-50. Can negotiate. SN1, SN2 is depend on the second factor. Okay. Okay. The second factor, which is the effect of nucleophile, which is a strong nucleophile or weak nucleophile. Okay. Okay, strong nucleophile is usually favor. Anybody who have highlighter, you can highlight here. Favor SN2 reactions. Strong nucleophile favor SN2 reactions. Check again, chapter 2 about this one. And also for the weak nucleophile, okay, weak nucleophile, usually water, alcohol, it's favor SN1 reactions. Okay, but they are not competing for the SN2 reaction. Okay, so consider what happened to the secondary alkyl halides, okay, which can react by both mechanism is treated with either their, okay, for the second carbocation, second alkyl halides, you have to consider the second factor, which is a effect of nucleophile. Okay, so if they are going with the OH, which is the strong nucleophile, will give you different products. And if they are going for the, this one is the second alkyl halide, okay, second alkyl halides. Or if they are going to weak nucleophile, it will give you different products. So for the predicting SN1 and SN2 nucleophile, okay. So for the strong, anybody who have highlighter, you can highlight here. Strong nucleophile favor SN2 mechanisms. Okay. So I have inversion configurations. Okay, this is second alkyl halides. Okay, which is one-step reactions. Okay, so if you have a pen, you can read key concentrations Rx. Okay. Just make additional notes, okay, and okay, for this one, okay, for the second one, weak nucleophile, anybody who have highlighter, you can highlight here. Weak nucleophile, we go for SN1 mechanisms. So this is very important because they are formed carbocation. As we know, as a SN1 reaction, so they are form carbocation first, second nucleophilic attack. Okay, this one is the first one. Okay, they have empty orbitals here, so they have probability to attack from the top, above, and from the below. Okay, and after that, they will give you different products. Okay, which is cis and transisomer. Okay, and also the rate. Just make additional notes. K concentration depend on alkyl halide only. If I say it, I will increase 2 times nucleophile concentration, so it's mean the reaction doesn't affect because it's depend 100% of the concentration of alkyl halides. Okay. So the third one is effect of living groups. As I said, beta living group increase rate of the both SN1 or SN2 rations. Okay, by differentiate the alkyl halide, we cannot differentiate whether they are favored SN1, SN2. Right now, they have two effect only. We can refer as a SN1 or SN2. The first one is the alkyl halide. The second one is the nucleophile. Okay. So for the solvent effect, the effect of which is number four here. Okay, so polar protic solvent, anybody who have highlighter, okay, favor SN1, okay, because the ionic intermediates for both cation and anion are stabilized by solvations. Okay, polar aprotic, it's favor SN2 reactions. This is very important. Okay. And also, okay, as a summary for predicting of the SN1 and SN2 reactions, okay, what we can say here, okay, methyl, this is methyl. This is primary alkyl halide is favored SN1 reactions. Okay, if we talk about nucleophile, we refer as a strong nucleophile, which is OH minus or OH minus, usually like that. Or another OR minus. Okay, it's a strong nucleophile. It's positive for the aprotic solvents. Find the example of aprotic solvent from early slide in this chapter, so you can find it. Okay, for the tertiary alkyl halides, okay, it's only favor of SN1 reactions. Okay, by the weak nucleophile. Weak nucleophile usually as a water or alcohol, or OH. Okay, SN1 also involved inversion configuration. Okay, this one as a racemic mixture. Okay, and usually positive with polar protic solvent. Okay, for the secondary, there can be SN1 or SN2 reactions, but depend on two. Okay? The first one is nucleophile. Okay, strong nucleophile. Anybody who have later favor SN1, SN2 reactions. Okay, strong nucleophile, SN2 reactions. Okay, for polar protic solvent, favor SN1 reactions. Okay, they have four effects that you have to consider for this predicting SN1, SN2 reaction. The first one is the types of alkyl halide. Second one is the nucleophile. The third one is living groups. The last one is the solvent, whether they are protic solvent or aprotic solvent. Okay, anybody who are from biology school, so you will learn about this one because okay, in nucleophilic substitution reaction in biological systems, okay, as we know, this is adenosyl methionine. Okay, they will give an example here in our body. So this reaction called methylation because CH3 group is the transfer from the compound to another nucleophiles, and it will give another products. Okay, so another example for SN2 reaction in adrenaline system. So okay, the adrenaline synthesis occur in interior of adrenal glands. Okay, in our body, so they will have noradrenalines, and after that become adrenalines. Okay, sometimes if you have stress or if you are in danger or frightened, sometimes the adrenaline will come out from your bodies and give you some different sensations. And sometimes it is good to have a middle range of adrenalines, not too high. So it's better to control your adrenaline if you can, because it will increase the rate of heart and also increase the blood pressures, and your blood vessel will be bigger during that time. Okay. Okay, for the vinyl and aryl halides, this is very different topics. Okay, SN1, SN2 reactions occur. You have to be understands about this one. Wait, I don't know what's happening. Okay, SN1 and SN2 reaction occur only sp3 hybridized carbon. Okay, vinyl and aryl, which is referred as a compound below. This is a vinyl A. This is aryl B. Okay, which have halogen attached to the sp2 hybrid carbon, do not undergo SN1 or SN2 reactions, because you have to follow the first rule, which is sp3 hybridizations. Okay, heterolysis of the CX bond will be formed highly unstable for vinyl and aryl cations. So in organic synthesis, I will talk about this one in the next class, and after that we will do some exercise. I will provide you the set of questions after this. Let me take some time to prepare, and after that I will post in e-learnings, and hopefully you can do it, and after that we can do it later together. Okay, anybody will have question before we finish? You can text, you can talk if you want. Yeah, do you have any questions to ask before we finish? No? Okay, it's okay. That's all for today, class. I hope I can see you on on Wednesday, and we will discuss about the exercise, and also and so on. Okay, and also take care, and see you on Thursday. Okay.